Hello, my name is Bovermann from the Rotting Sounds project. Together with Dario Sanfilippo, I looked into what we call bitstream synthesis with Faust. Although a widespread assumption is that forms of digital representation are absolute and perfect in both as storage and reproduction, everyday observation shows that degradation and decay does indeed happen on all of the many levels of digital data handling. In our artistic research project Rotting Sounds, we therefore explore artistic opportunities arising from obsolescence, degradation and information loss in digitally represented sound. Within the research project, we are particularly interested in how digital audio decays and the aesthetics of such decay. Before diving into this from the perspective of bitstream audio, I'd like to introduce you a little to how we interpret digital audio or digital material. We differentiate between three or actually four elements that compose digital material: hardware, data and interpretation. Hardware here are the machines on which digital computation takes place. This might also be a human computer. Data are the actual zeros and ones, and interpretation is the semantic of the data. That means how the data is stored on the machines and how it needs to be interpreted in order for us to understand it. For this talk, however, we'll focus on the data interpretation part. In case of digital audio, we need to know, for example, how to turn digital data back into a signal. This can be done, for example, as in PCM, where we interpret data as a bunch of floating point values or integers that represent pressure level changes over time, or as energies or frequency bands, as it is done in Fourier transforms based representations or MP3, for example. Digital degradation has some special features that we'd like to look at. Compared to the gradual and graceful degradation and eventual disintegration of analog sound generation and reproduction appliances, think LPs and their players and their decompositional crackling, digital tools such as PCM or MP3-based representations tend to exhibit an abrupt breach into fail and thus silence or noise. That's what you see there in orange. 1-bit based information representation for audio are an exception to this and are thus of particular interest in terms of our digital deterioration research. Why this is, I will show you now. In difference to pulse code modulation streams, so PCM, in which a bit can have one or several meanings only determined by its position in the serial bit stream, a bit in a 1-bit stream always carries one and the same kind of information. A 1-bit audio representation or delta sigma modulation thus minimizes the possible interpretations of a single bit to be either up or down. This means that both deterioration in the time domain, that means jitter, and the sporadic misinterpretation of the value of a bit, that means a bit flip, has only a minimal effect on the sonic outcome. Sterne's cliff, that we saw before, is as wide as in the analog domain. So delta sigma modulation is an analog to digital encoding technique in the 1-bit domain with a nonlinear quantization noise distribution. An elementary DSM design consists of integrating the quantization error, the difference between the output of the modulator and the input signal, and subsequently processing the result through a comparator to output a maximum or minimum value. The outer negative feedback loop in the DSM acts here as a noise shaping transfer function that pushes the quantization noise towards the upper region of the spectrum. The order of DSM systems is determined by the number of integrators in the network. Hence, oversampling becomes very efficient in order to move the quantization noise away from the audible range, although high oversampling ratios are required for low-order DSM designs for adequate signal-to-noise ratios. On the other hand, first-order and second-order DSMs, as you see them in these diagrams here, guarantees stability for a wide range of input signals, whereas high-order DSMs may result in unstable behaviors. Digital low-pass filters can remove the quantization noise from the ultrasonic range, and downsampling can then be performed to operate at standard sampling frequencies. Digital DSM can be deployed to convert multi-bit signals into 1-bit ones. For the inverse, the conversion between 1-bit streams to multi-bit ones is simply carried out by averaging the pulses in the 1-bit stream, which can be achieved effectively through low-pass filtering. Specifically, the cutoff frequency of the low-pass filter determines the range of the baseband, whereas the bit resolution of the coefficients of the filter determines the bit depth of the resulting multi-bit signal. Before diving into the functionality of the BitDSP library itself, we introduce 3 data structures. Integer-based, bitBus and int32 they are called. And these are interesting for 1-bit sound synthesis, or we think that they are interesting for 1-bit sound synthesis, and we therefore use them in our implementations. While the first technique is a straightforward representation based on standard operators and signal flow, the latter incorporate oversampling and bitwise operation techniques which require redefinition and unfolding of feedback paths. Overcoming this challenge, however, results in a more optimized implementation that allows for most of the time necessary oversampling and compact representation of data structures. So let's look at them in a little bit more detail. A straightforward implementation is the integer-based one, in which each 1-bit sample is represented as an integer value that is either 0 or 1. This representation allows to implement bit-based operators utilizing standard operators from the Faust library. For real-time applications, sample rates are, however, limited to the maximum sample rate supported by the audio interface, which is quite low, so we actually want to be in the 3 MHz range, at least, when we are talking about 1-bit audio or DSD audio. Another limiting factor is that each 1-bit value is represented by typically 32 bits, so computational and memory allocation is far bigger than necessary. Then there is the bitBus representation, which introduces parallel processing of parallel bit streams. So here the bit stream is represented by an n-dimensional signal bus of n consecutive samples of the bit stream in n parallel streams. And this results in an oversampling relative to the sample rate by a factor n. And this is kind of nice because we have oversampling here, but this approach requires unfolding of feedback paths over the n signal buses, which means that the standard implementations of the Faust libraries that utilize feedback operators cannot be integrated. Instead, we need to write specific versions. And how is this done? So if we have here on the left side a feedback-inducing operator that we call f, then we need to kind of unfold this operator. So the feedback needs to be unrolled for the amount of bits. So we have here a bitBus of size 3, and yeah, the feedback needs to be unfolded. We have implemented this for some of our algorithms, but it would be really nice to have some kind of automata solution for that. So the int32 representation is kind of going one step further. So here we are doing a parallel processing in a compact bit representation, and which means that the bit stream is encoded in a Faust native integer signal as a sequence of bits that need to be processed in parallel. For now, an integer in Faust typically translates into a 32-bit signed integer, which makes implementations actually quite difficult. But they are also implemented or equivalent to the bitBus implementation with n equals 32, which means that the resulting upsampling factor is 32. Essential for operating in the 1-bit signal domain is to provide a single sample delay, while its implementation in the other formats is closely related, if not the same as in the standard Faust library implementation or in the standard Faust implementation. For the IN32 case, we had to do some bit shifting, which you see here, and it was quite something to figure this out for me at least. So here it is. Straightforward operators for the IN32 representations are, for example, also bit and, bit or, and bit not, where the latter is strangely not implemented natively in Faust. Other operators are, for example, left shift or right shift, for which we also had to rely on external functions because right shift operators are unfortunately not really well defined for signed integers. I'd like to generalize what we looked at for now by introducing the notion of bit streams based on the Sterne's cliff that we saw a few slides ago and here also in the lower right. This will hopefully help you to understand our reasons for implementing some of the following algorithms. A bit stream, as we define it, operates on bits over time, and its degradation has similar effects on each bit, no matter of its position. So we are not assuming any kind of time relation. So further, there are no differentiations to be made regarding the interpretation of bit streams. And in BitDSP, we therefore differentiate between basic bit-based operators with no time-based context but a previous state. Delta sigma modulation, which we've seen already, where each bit is embedded into a stream of other bits, forming a signal. And approaches that generate, respectively, operate on parallel streams of bits that unfold parallel in time. Examples for such operators are shift registers or one-dimensional cellular automatas or random Boolean networks. Some of them I will show in the talk. Others are in the paper. You can read about in the paper. As in other DSP environments, bitstream operators, independent of the previous differentiations, may roughly be categorized into generators, filters, and converters. Kind of straightforward. Apart from the last one, converters are operators that are intended to be used to translate semantic information, for example, denoting a waveform from one representation, for example, PCM, to another, for example, 1-bit audio. Or from the IN32 format that we introduced into the bitBus format, for example. With this in mind, block-based operators that only operate on a certain part of the stream might make sense. So these block-based operators assume a certain amount of surrounding bits to be their context of operation. This makes sense, especially in bitBus and IN32 form, since here n, respectively 32 bits, are processed in parallel and are thus available for the operator. One sonically or easily available for the operator, for the function. One sonically and functionally interesting operator to implement is applying a bitwise operation only to specific bits within the block. For example, via bit mask here, indicated in yellow. For parallel bit streams, we found it interesting and surprisingly versatile to be able to interpret part of a state as integer-based PCM values. We therefore implemented bitDuck. It allows to select a range of parallel bits in a bit stream and interpret them as part of an integer PCM value. As with most definitions, this bitDuck has parameters and they can be modulated at audio rate, which can result in interesting sonic behavior as well. From the perspective of an artistic researcher into rotting sounds, a simulation of bit rot is also beneficial to have in order to induce errors into a stream. We implemented such bit-related degradation of the bit stream with this bit rot definition, which under specified likelihood and depending on its type parameter either sets a bit's value to false, true, or reverses or flips it. Now we're coming to something that's a little bit more interesting, or more complex, which are bit shift registers. So hardware shift registers are in widespread use, for example, for cryptography, hardware-based indexing or counting applications in which speed and efficiency are important, possibly because of the easy availability of shift registers as integrated circuits. Several sound synthesis-related hardware implementations of feedback and shift register-based filters, sequencers, and oscillators have been developed, most prominently in the Wrangler circuit by Rob Hordyke, which, if you don't know any of his stuff, I really would recommend to check him out, and Grant Richter's Noise Ring. And also Laura Mills' Double Knot has a shift register in it, which takes a prominent role. Linear feedback shift registers are a special case of shift registers that are used particularly often also in the industry and for space applications. Their theoretical framework is thus well understood. An LFSR shifts for each block trigger by one position, and the new state shifted in here on the left is determined by computing the parity, that means the recursive OR of selected slots of the register. The length of the register as well as the selection of slots used for calculating the newly inserted bit determine the periodicity of the system, and we implemented a variable length LFSR in the IN32 style that makes use of the bitDuck implementation to sonify parts of its state. Finally, I'd like to briefly tell you about the performance I did with the BitDSP system, or with parts implementations based on the BitDSP system this year at Ars Electronica Festival in Linz. Together with Katrin Hunzer and Thomas Grill, I performed the piece Merge and Dissolve. And since we are all, or Thomas is part of the Rotting Sounds project, and this was part of the Rotting Sounds project, we investigate 1-bit audio as a medium in which deterioration may take place. We focused on the aspect that an electrical bit stream can simply be played over a normal amplifier loudspeaker combination, yielding the analog sound equivalent of the sonic information embedded in the bit stream. With this in mind, BCM-based audio processing strategies, as well as strategies introduced in this talk, were integrated into the signal network between the performers, giving rise to rather unexpected sound qualities. While the overall setup of the performance was highly networked and tools of the individual performers were independently developed by us and in various forms of hardware and software, my performance system relied on a supercollider-based performance setup that utilized custom-built Eugens written in Faust and the BitDSP library. As a conceptual and possibly also practical decision, we as a group agreed to play at a sample rate of 192 kHz, allowing the use of standard audio hardware and software and residing in the somewhat fuzzy intermediate between common PCM-based sample rates and proper 1-bit sample rates. My interaction with the system was handled with a monohm grid 128 controller, and here I had it upright, so in portrait, and while the lower 8x8 matrix of button of the controllers was used as a switchboard to route the 8 incoming signals to the respective outputs. That's here in the figure, the crossings in the lower left of the diagram. The upper 8x8 matrix of buttons served as switches to activate or deactivate signal effectors. That's the EFX in the diagram. So, although we are still at the beginning of our research, we are happy to say that Faust and its community turned out to be a welcoming environment for implementation of and discussion about a broad spectrum of bit-based operations. I'm really happy about this personally, and this is kind of my first deeper dive into the Faust language. Unfortunately, I have to say that since implementations of many of the described functions depend highly on specific bit representation of integers, in our case the unsigned fixed width integer type uint32, the lack of such an unsigned integer type and generally the lack of data types with a defined bit length renders some implementations in native Faust code impossible. And so in crucial situations, we had to rely on the use of the f function primitive to include external C headers. That's, of course, suboptimal. We would therefore be very grateful for the inclusion of standard types, for example, according to the C++11 standard. Apart from a growing repertoire of applications and performances, Dario and me are looking forward to include more bitstream related functionality into the library, and we eventually intend to offer a library that facilitates bitstream DSP for use in development with a particular focus on distortion and deterioration processes. The starting points implemented so far are performant and powerful due to core functionality provided through the language toolchain, and most importantly, you basically that are sitting here, or the Faust community. We are therefore very grateful for feedback on the existing implementations, so please have a look at it. It's on GitHub. It is open source based on the MIT license. And please get in touch if you're interested. Thank you very much.